Welcome to Naked Reflections, brought to you from the Wolf Institute. I'm Ed Kessler, and each week I'll be taking an in-depth look at the stories reported by our friends over at the Naked Scientists. What does the latest scientific stuff mean for the rest of us? Stay with us and find out. Imagine a world where nothing exists until it interacts with something else. A world of ghost waves, distant objects that seem magically connected, cats that are both asleep and awake. That's the mind-blowing world of quantum, a theory that's nearly 100 years old, has practical applications in everyday life, but which is still an enigma for most of us. And it's the subject we're grappling with this week on Naked Reflections. The physicist Francesca Day described one of the mysteries of quantum, that is, entanglement, in the Naked Scientist show Disney, Dark Matter, and Deja Vu.
Now, it's possible in an experiment to have, say, an atom emit two photons at once, such that they have to have their polarizations pointing in opposite directions. When we do this, and say the photons travel to opposite ends of the world, and then we measure one of them, and it's pointing in a particular direction, then we measure the other photon, and its polarization will always be pointing in the opposite direction, because those two photons are then entangled. And this happens instantaneously. So it's very mysterious how the information can travel from our measurement of one photon instantaneously to our measurement of the other photon.
We've got a distinguished panel this week. Carlo Rovelli, a theoretical physicist and author of a new book called Helgoland, named after the treeless island in the North Sea where Werner Heisenberg retreated to think about some physics in peace and quiet, and came up with a theory of quantum mechanics. Joining Carlo is Richard Staley, Hans Rousing Reader in the History and Philosophy of Science at the University of Cambridge, and a biographer of Einstein and his community. Now, Einstein was a man who had his own brushes with quantum, and Richard has a particular interest in physics and anthropology. Well, let me begin by asking the question, why should we be interested in quantum mechanics? Why should the average taxi driver be interested? Carlo, I think you've already had this question from a taxi driver in Italy.
I don't think anybody should be interested in anything. I mean, nobody has to be interested in music. Nobody has to be interested in sport. Nobody has to be interested in what happened next door. But I think we are curious. All of us are curious. Cambridge professors, taxi drivers, radio people, all sorts of people. We want to know.
It's a good reason to be curious in general, but why should we be curious about quantum?
Because it is a evolution in the way we understand reality that has dramatically changed what we think about matter. What is matter? What are the things around us? How are they made? Somehow, with physics, with classical physics, with Newton, Maxwell, and so on, and even Einstein, we got an idea that the world, at some level, is relatively simple. Just some space around, and in this space there are some particles that move around, perhaps some fields that move around, perhaps space itself might bend, we learned. But that's it. There are things out there, and they have some properties, and each one of them does whatever the laws of physics tells it to do. It was a relatively simple and actually spectacularly successful image of the world. There was a time not long ago, 100 years ago, in which it seemed that that was it. We have got the key for understanding reality, so to say. We have seen how the world is made. It's made by just these particles, these fields, and that's it, and obeying equation. And then came quantum physics, namely a set of discoveries, a set of observations that just don't fit with this picture, which forced the physicists of the early 20th century to change this picture, to give up this picture to something dramatically different. So here is a typical example of the strangeness of quantum mechanics. If there is a particle like an electron on one side of a wall, and in the wall there are two little holes, two slits, it's possible that the particle goes through and we find the other side of the wall. Now, in our intuition, if there are two holes, it goes either through one or through the other. But when you do the quantum calculation, it goes through both. And if you assume that it goes only through one and not the other, you do the calculation, you get the wrong result. You don't get the right position where the particle arrives, the other side. So this is something completely mysterious, because we see the particle on in one position, again, the other side of the wall, but in between it seems to open up. And that's when we say there's a duality wave particle, right? Because we always see the particle, but in our calculation, we treat it as a wave. It opens up, it goes to both holes at the same time, and then we find it the other side of the wall only in one position. And if you go in a laboratory of physics, you actually see this incredibly phenomena, and you say, come on, it's impossible. You're cheating me. You're not cheating me. That's how nature works.
So, Richard, quantum is not a recent concept, but we're still grappling with it, as Carlo's just told us. Can we wind it back a bit and take a long view of how our concepts of matter and the universe have evolved?
The Greeks are really famous for having speculated about the ultimate constituents of matter. And Democritus argued everything is composed of atoms, which are indivisible and perfectly solid, no internal gaps. They move in an infinite void. They repel each other when they collide, but they might grab onto each other with hooks and cluster together. That's a view about ultimate substance, and it relates to the perspective that Carlo was talking about. People have often looked for ultimate substances, and it tries to explain how change can result without requiring the creation of something from nothing. And that's a really interesting thought. Plato brought a mathematical perspective on those fundamental constituents. He thought that the 5 regular polyhedrons described the substances of the universe. The next moment I want to move to is much, much later, in the 1860s. It's perhaps in the period that Carlo was thinking about as one where people were feeling certain about Newton and the like. And I want to look at one of the first people to raise real questions about Newton's work. And that was the Austrian physicist Ernst Mach. And he had a problem with Newton's first law of motion, the principle of inertia. That law is a very simple, clear one. Every body remains at rest or in uniform motion unless acted on by an external force. That's how it's usually stated. And Mach said that law is undefined unless you specify in relation to which body or which frame of reference any given body remains at rest or in uniform motion. Relationships are critical, he said. And if you think of 2 alternatives, one is of the Earth rotating around its axis in the sphere of the fixed stars, or if the Earth remains stationary and the fixed stars revolve around them. One is the Copernican picture, the other is the earlier picture. Geometrically, they're the same, but astronomically, the first one is simpler, and in Newtonian theory, the first theory also has a different consequence. The motion due to inertia means that the Earth would bulge. It would deform in shape. And there'd be the deviation of a pendulum on the surface of the Earth. And for Newton, that was explained by motion in absolute space, rotation in absolute space. But the situation is absolutely the same. The relative motion is the same. And Mach couldn't bear that idea that you would have a different kind of explanation because of absolute space. He didn't accept absolute space and argued the principle of inertia should be altered to reflect the part that all bodies, near and distant, play in the law of inertia. So you have to take into account the fixed stars when you think about the body on Earth. Now that sounds really philosophical, but he came to that line of thought after working in physiology and understanding how we move about on the Earth and understanding what makes things look vertical or how we know that we're standing upright, and how we hear and see things when we're in motion and so on. So there was a mix of physiology and psychology and physics that led Mach to move through different spaces before he got to critiquing absolute space. The third moment is 17th of March 1905, when the young Albert Einstein sends his first really major paper off to the Annalen der Physik. It was on what he called a heuristic point of view concerning the production and transformation of light. And he said in the beginning of that paper there's a profound formal difference between the way we think about gases and other material bodies and Maxwell's theory of electromagnetism. The state of matter looks as though it's determined by a large but finite number of atoms and electrons. But in contrast, we use continuous spatial functions determining electromagnetic states. So the wave theory works brilliantly for optical phenomena, and it probably won't be surpassed, he thinks. It's an amazing theory, but where you do look at production and transformation, you can see that light behaves as if it were a particle, and the energy of light is quantized. That's an extraordinary thought. He knows it's revolutionary, and hardly anyone believed it.
Einstein was one of the people who contributed to the birth of quantum mechanics, as Richard is saying. So a lot of the ideas of quantum mechanics come from Einstein. Quantum mechanics had a long period of birth through the work of many people, all during the first 20 years of the 20th century, and somehow exploded in its the form that we know in 1925, 1926. And one of the key person who sort of found the key to understand how to make it work is Heisenberg, on the island of Helgoland, which is the title of my book. Heisenberg was a brilliant young German physicist who was a good friend, Wolfgang Pauli. The two had somehow learned physics together, and the birth of quantum mechanics is in part due to their friendship. And Pauli, godfather, was Mach. The father of Pauli was a very good friend of Ernst Mach. So Pauli knew very well all the philosophical ideas of Mach, who had a direct influence on him and on Heisenberg. Heisenberg found the key with a group of other friends, most of whom were in their 20s, wrote the theory that today we call quantum theory, using a lot of Einstein ideas. And since the very beginning, the theory was very mysterious. It looked very strange, precisely because it did not look in the way that Newtonian physics looked before. And the key novelty was that it was not about how a physical system behaves, but it was about how it looks to us, how we relate to it. And we see some Mach ideas here in some sense, is how the systems enter in relation to us. And this is in the very mathematics. The mathematics of Heisenberg was not a description of the position of the electron in the atom. He was studying electrons in the atoms. The atom is a constituent of everything. So it's basically of everything. Not the position of the atom itself, but where we see the atom if we look. And the mathematics was giving the prediction of where we see next the atom after a while that we looked, without telling us what happened in between. Einstein, who had been important to get there and had suggested some of the ideas there, including the fact that probability plays an important role here. We don't know exactly where we're going to see the electron next. We only know the probability where. Einstein resisted that. He said, oh, come on. We are giving up too much about our very concrete view of reality. And Einstein never questioned the importance of the step of quantum mechanics. He was obviously perfectly aware that there was a lot of right. In fact, it's Einstein who proposed for the Nobel Prize Heisenberg and Jordan and Born, who were the actual inventors of the theory, the first inventors of the theory. So he immediately saw that this was a deep step ahead understanding the world. But it was so strange, and it would contradict the direct realistic pictures that Einstein had, that he thought it was sort of an incomplete or not yet coherent or to be better understand theory. And we still are in that situation. We still have a theory that works perfectly well. It's used by everybody. Quantum mechanics is not some exoteric theory by a group of scientists in the laboratories. It's used by chemists, it's used by engineering, it's used to make computers, to build apparatus for medical, like the magnetic scanning things that the doctors used to look inside our cells, used to nuclear plants. The nuclear bomb was used quantum mechanics, unfortunately. It's used in astrophysics, it's used everywhere in science, but it's used like a black box where you input, is a mathematic that you input what you see, and then it predicts what you're going to see next. And of course, if you want to build a computer, that's good enough. You build a chip, and there's something inside, and you have a theory that tells you if this happened, then that's happened. But if you want to know what happened in between your observations, the theory doesn't tell you what it is. And from there's a huge discussion today, which is not ended yet, about what this theory means. And we go back to Mach here, because I think a lot of the correct way of thinking about what the theory means is precisely to think in terms of relations and not of things.
I think that's really right, Carlo. And one of the things that strikes me, given the way that Ed introduced the session, is how interesting it is that someone who moved between physics and psychology and physiology was so clear about the significance of critical relationships and understanding the role of the observer. And that had to emerge in a slightly different form in the development of these theories that were looking at the atom, where it was mathematized and where it was located in questions of energy and time and position and momentum.
So here is the key point, in my opinion. It seemed that the observer is playing a role, right, in nature. I mean, how does nature know if there is a scientist with a PhD in the laboratory that does something or not? I mean, nature is not supposed to work differently if there's a scientist or not, if there's an observer or not, if there's a human being or not. I mean, nature just follows its own ways. And whatever happened here presumably happened the same on Andromeda, where there are no observers. It's not the observer as such that makes a difference. One could say anything can be regarded as observer, because what nature is about is not how atoms or stuff look to us. It's just how atoms and stuff interact with something else. But instead of thinking how an atom is, we should think of how an atom interacts with something else. So we should always think about the relation between two pieces of the universe. And one special case is when there is a scientist making an observation. So one piece of the universe is the atom, and the other piece of the universe is the scientist. But if we use the same logic generally, I think what quantum theory is telling us is, look, we understand nature better if instead of asking how things are every moment in time, we ask how they affect one another when they interact. So if we think in terms of interactions rather than in terms of single substances with properties.
Well, what I do observe is time is moving on, and we're going to have to take a halfway break. This is Naked Reflections with me, Ed Kessler. My guests are Carlo Rovelli and Richard Staley, and we're discussing the small matter of quantum. It's a difficult thing to get your head around, but it seems to have practical applications. Here's the naked scientist Lizzie Clark in deepest Sussex.
The key to this quantum computer is that its circuit can operate by not just being on or off, like a switch, but by occupying a state that is both on and off at the same time. This is down to quantum mechanics, which allow very small particles to be in different places simultaneously, where they stay in these states until they are either observed or disturbed. It's a bit like flipping a coin. The coin is both heads and tails when it's in the air, but it's only heads or tails once it's caught.
So let's discuss the practical applicability, if you like, of quantum. And I think you mentioned quantum computing. How does that actually work?
Yeah, there's a lot of excitement about quantum computing. Definitely, it's a possibility. There are already some quantum computers that have been built. In fact, you can go online on the IBM website and actually use a quantum computer. It's not too hard to learn. They work using quantum mechanics, so they work using the strangeness of quantum mechanics and precisely the fact that there is this theory that tells you what you input in the computer when it comes out from the computer without telling you what happens in between. And in some sense, in between, one can view as many things happen at the same time. That's the magic of quantum mechanics. So a quantum computer works like many computers working in parallel at the same time, so to say. And this, it can be proven, in principle permits us to do calculations that we could not do with usual computers. So that's, of course, very exciting. Now, I also must say that, billions of euros have been put into that. Is not yet working very well, and it's not obvious that it will work, because quantum mechanics is very fragile in a sense. It describes perfectly well the small things, but as soon as you go to big things, the quantum effects disappear very rapidly because they're diluted into the many atoms and molecules. So to see the quantum effects, you have to sort of isolate things well, and that's not easy. To me, what is interesting in quantum mechanics, and I think also to Richard, and I think also to the people, it's not just that it has great applications. Of course, it has great applications. I mean, the laser is a great application, but it's conceptually extraordinarily new. And I think the fact that we understand at the level of physics, so this elementary grammar of nature, what matters are not how things are, but how they relate to one another. This, I think, has an impact that goes far beyond physics, because it touches all of us. It touches all the scientists. It's also touching our everyday life. If, for instance, if we think at ourselves, not as entities, but as nodes in a relation, I believe we think better about ourselves. I am the number of people with whom I interact, the things with whom I interact, the memory, the history I have by myself. I am this network of things, not a single entity.
Well, let's pick up on that interaction, because you're moving into a space that I personally feel more comfortable with, which is this one about the relationships that we have. And there's a pre-medieval 4th century Buddhist philosopher called Nagarjuna, who apparently seemed to anticipate quantum in some respects. And that's the fact that we are all interlinked, that we all relate to one another, that properties exist only in relation to something else. Now, from an anthropological point of view, Richard, as well as an expert in physics, that really says something pretty profound to all of us, even a theologian like me.
Yeah, I'd agree. And thinking about someone I've looked a lot at, which is Ernst Mach, one of the things that's really interesting about him is how he tried to work with that insight in understanding of man and the soul and understanding of matter and the universe. And he actually tried to do that with a methodological rigor. And that's, I think, very important in thinking about these areas. So he would never say, just look for relations. He would say, look for the unrecognized relation. Look at the assumptions that you are not aware of. And therefore, you need to look from matter on Earth to matter in the distant stars and look for the connection between them. Don't look for fundamental substance. Look for the unrecognized relationship. And he expected there to be a continuum. Matter is related to all matter. The human soul, he thought, is not principally, or certainly not solely, and maybe not even principally, a matter of the individual ego. It's actually determined as much by the environment in which it lives and moves.
Yes, you mentioned Nagarjuna, the Buddhist philosopher of 2 millennia ago, actually. It's not very well known in the West, and I didn't know him before reading his book a few years ago. But he's extremely well known in the East. In fact, he's one of the main classical thinkers in Eastern thinking, sort of like Aristotle for us. I would not say that he anticipated quantum theory, because that would be an anachronism. And of course, he didn't know anything about atoms and quantum. I don't think this is the point. I think the point is that philosophers offer us scientists and us people interesting conceptual structures that then may work well in this and that situation. And what I found astonishing in Nagarjuna is this radical relationalism. As you were saying, Nagarjuna is proposing a way of thinking of the world in which we give up the idea of looking for the ultimate substance, whether it is matter, whether it is the soul, whether it is the spirit, whether it is God, whether it is observations, whether it is social construct, whatever you think. I mean, you can look at the history of philosophy as searching for the ultimate substance and on which to build all the rest. In Nagarjuna book, it's a series of short chapters in which he takes all basic ideas on which to ground the rest, and he shows that each one of these ideas actually needs something else to make sense. He calls this fact that every single idea or substance of whatever cannot exist by itself, he calls this emptiness. So he says this pen is empty, meaning not that it doesn't exist. Of course it exists. It's a pen. But it's empty if I try to think at it independently of everything else. It's empty of autonomous individual existence. And then this incredible final, toward the end of his book, this chapter, he says emptiness itself is empty. Namely, if you try to use it as a fundamental ground for understanding, I think it doesn't work. I was struck by it because in trying to reflect about quantum mechanics and the fact that quantum theory seems to forbid us to think at object by themselves, independent of the interaction. I mean, if I look at philosophers, is there a way to think radically that everything depends on anything else? And of course, there are these ideas all over. I mean, there are even, you're a theologian in Protestant theology, there are ideas of radical relationalism, reading of Trinity in this sense, and a lot of things. But so clear and clean as in Nagarjuna and complete, I've never found anywhere. And I found it deeply useful for me, at least, and convincing in a sense.
But I do also have a question. And one of the things that people often ask is, are we still searching for a theory that unifies relativity and quantum theory? And I wonder, and I'd like to know Carlo's thoughts on this, whether that way of thinking may in fact be the wrong way of thinking. If things are relational, maybe you're looking for a relationship or a common connection rather than a unified theory.
It's a very good question, Richard. I've spent my life trying to search a unified theory of quantum and gravity and space-time and Einstein theory. We have some options. And I believe that where we are now is not that we don't have that theory, is that we have more than one options and we don't know which one is the right one. And the option which I find more convincing, which is loop quantum gravity, is deeply relational in itself. So it's not about entities. We don't want a unified theory. We want a harmonious way of thinking altogether. Not because it's going to be the final theory of the world. I don't believe in the final theory of the world. But because it's sort of the best we can do today for bringing together everything we have understood about nature so far.
We need to draw to a close, and I know the subject is going to go on and on and on again. Thanks to my guests, Carlo Rovelli and Richard Staley. And perhaps it's worth pointing out that however difficult we may find it to solve the mysteries of quantum, nature seems to have already solved some of them for herself. Well, thanks for listening to Naked Reflections. We'd love to hear from you. You can contact us at the Wolf Institute by email or on Facebook. Let us know what you think of the show. We've covered a wide range of subjects, which you can find by delving into our back catalogue. And it's worth checking out our new podcast, The A to Z of the Holy Land, From Arab to Zion, All You Need to Know About the Middle East in bite-sized chunks. You can also find the Naked Reflections podcast at nakedscientists.com/reflections or wherever you get your podcasts. I'll be back next week with some more guests.